guys. Dalton's Law of Partial Pressure. This is section 5 of the gas law chapter. Let's go. Dalton's Law of Partial Pressure. For a mixture of gases in a container, the total pressure exerted is the sum total of the individual pressures that each gas would exert if it were alone. I feel a picture coming on. So let's say you have a box with 3 different gases in it. Gas number 1 is going to be blue molecules. Gas number 2 is going to be red molecules. Gas number 3 is going to be, really light blue molecules. If you look at this container of 3 different gases, you will notice that the pressure of the entire mixture will be the sum of each gas individually. So what did I have? I had a red one, and I had a blue one, and I had a light blue gas. So each gas will still exert its individual pressure, but the pressure of the entire mixture will be the sum of them. And they don't necessarily have to be in the same quantity. You could have more red than blue or more light blue than either two. All right, a couple of different calculations that accompany Dalton's Law. Number 1 is the easiest, which I just showed you. The total pressure of a mixture will be the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. Mole fraction. Mole fraction is number of moles of gas number 1 over the total. You will notice this is technically part over whole without multiplying by the 100%. This will be in a decimal form, not fractional. Even though it's called mole fraction, don't put it in a fraction form. It's in a decimal form, and it's basically going to tell you what percentage, and I'm doing air quotes here because it's really not in the percent form, it's in the decimal form. It's going to tell you how much of gas number 1 you have in your mixture. Mole fraction can also be calculated using pressure. The pressure of number 1 divided by the total, also part over whole without multiplying it by 100%, also decimal form, also no units. Now here's a little mathematical term. If the mole fraction is equal to number of moles of a individual gas over total, and mole fraction is also equal to pressure of the individual gas over total, then it stands to reason that N1 divided by N total will be equal to P1 divided by P total, which of course is completely logical. Mole fraction is the ratio of number of moles of individual gas in a mixture to total number of moles. The mole fractions will add up to be 1 because of course it's in decimal form, not percentage form. So it can't add up to be 100 because 100% in decimal form is 1.00. Very logical. All right, examples. We have a mixture of helium gas and oxygen gas. 46.0 liters of helium gas at 25 degrees Celsius and 1 atmosphere, and 12 liters of oxygen gas at 25 degrees Celsius and 1 atmosphere are placed into a 5-liter tank. Now you're probably thinking, wait a minute, how are you going to get 46 liters of helium and 12 liters of oxygen into a 5-liter tank? How's that possible? 5 liters is smaller. Gases are compressible. You can smoosh them into smaller areas. So yeah, 46 liters of helium, totally going to fit into a 5-liter tank. They are compressible. And we are going to calculate the partial pressure of both gases and the total pressure of the tank. I have helium and I have oxygen gas. I have 46.0 liters of helium and 12.0 liters of oxygen gas. Helium first. The number of moles of helium is going to be equal to Pivner. Our good buddy R, 0.08206 liter atmosphere moles Kelvin. In Kelvin is the temperature. I get 1.88 moles of helium. Do the same thing for the oxygen gas. Number of moles of oxygen gas. Pivnert. Oxygen gas is also at 1 atmosphere. Different volume. R is the same. Temperature is the same. And I get 0.490 moles of oxygen gas. That's what's in my mixture. The pressure then of the helium is also going to be used, Pivnert, because don't forget this 1 atmosphere here, this is the total. This is the total pressure. So now I want to find the pressure of each individual gas. So I calculated N using total pressure. R total volume 5 liters. Pressure of the helium in my mixture is 9.20 atmospheres. Going to do the same thing for the oxygen gas. Oops, R. Okay, something, I think I misspoke here. I'm going to say this is wrong. This was the 1 atmosphere before it got mixed together. And it's going from 46 liters to 5, so I would expect the pressure of the helium to go up, which of course it does. This was the pressure of the oxygen gas before it got mixed together, and it's going into a smaller container because it started out at 12 and went to 5, so I would expect it to go up also, which it does. So I think I misspoke when I said that was the total pressure earlier. It's not the total pressure. That's the individual pressures before mixing it into the 5-liter container. All right, so here are my partials, right? 9.20 atmospheres, 2.40. This is the partial pressure of helium. This is the partial pressure of the oxygen gas. And the total is going to be the sum of the two. Total is going to be the helium plus the oxygen gas, and that's going to give me a total of 11.6 atmospheres. So when you put them into a smaller, again, think about it, you're shoving 46 liters into a 5-liter container. You're shoving 12 into a 5-liter container. I would expect the pressure to go up, and it definitely does. The total goes up, the partials go up, So in that mixture, in that smaller volume, helium's 9.20 atmospheres, oxygen's 2.40 atmospheres. Mole fraction of nitrogen in air is given. Calculate the partial pressure of nitrogen in air when the atmospheric pressure is 760 decimal place torr. So they give you the mole fraction, and the mole fraction is indicated with a very fancy X. And they give me the mole fraction of nitrogen, and that's 0.7808. And mole fraction of nitrogen gas will be equal to either the number of moles of nitrogen gas over total, or will be equal to the pressure of nitrogen gas over total. I don't have moles, so I'm using this guy. So 0.7808 will be equal to the pressure of nitrogen gas, and I wrote it pretty poorly, didn't I, here, but I don't mind, and 760 torr. So the pressure of the nitrogen gas, that's how it should be written, sorry, is going to be 593 torr. Now let's do a little analysis on this. This basically tells me that 78% of this guy is nitrogen gas. And I'll bet 78% of 760 torr, which is 1 atmosphere, is going to be equal to 593. And the rest is the other gases. Example number 3. Partial pressure of oxygen was observed to be 156 torr in air with a total atmospheric pressure of 743. All right, so here's what it gives me. Partial pressure of oxygen gas is 156 torr, and the total is given as 743 torr. Well, this one's simple. Mole fraction of the oxygen gas is going to be the partial pressure of the oxygen gas over total, part over whole. You're just not multiplying it by 100, over 743 torr, and I get 0.210. So technically speaking, what it's saying in a roundabout way is 21% of 743 torr is oxygen. They're called mole fraction. Do not leave it in a fraction form. Put it in a decimal. Mole fraction is exactly the same thing as basically saying percentages, but they're not. You're just not putting it in percent form. You're leaving it in decimal form. Can't get any easier than that. And that's Dalton's Law really quickly.